So I'd like to solve this inductor transient problem where we have a switch that's shorted and opens at time equals 0. So first I'll solve it what I would hope would be an intuitive method where we really just look at where should it start, where should it end, and find out how long. Then we can do a more formal with Laplace. So the first thing we notice is that before that switch opens, right, this is shorted, all the current would be going through a loop. Then when it opens up, all that current goes through R1 and that gets split between R2 and L. So where this response starts at time equals 0 is easy, starts at 0, right? Um, where does it end? That's pretty easy too. So after the switch is closed, all the current goes through R1 and then it's distributed between these two depending on what the change in current is and what the change in voltage is. But something to remember is that at when there's no change, voltage across the inductor is 0. So voltage across the inductor equals L di dt. If there's no change, and we know from first order systems that they start someplace, they end up, and then they don't change, right? So if that's 0, then that has to be 0. And if this is 0, well, then the current has to be 0, right? So it'll end, in fact, at I naught, because if this is shorted, right, all the current coming out will go through that inductor. None will go through that resistance. So start in this problem is at 0. End is at I naught. Then the next question would be, um, well, how long is it going to take to get there, right? And in this case, I think it's a little bit easier to do it just looking at the natural response and Laplace. Because since all this current is going through R1 and being distributed through here, R1 is not slowing down or changing how this circuit charges because it's ideal. So really I just have to look at this. I did it pretty quickly where R2 equals the inductor current equals 0, substitute the voltages, right? Collect the voltage. In this case, the voltage can't be equal to 0, right? Because that's what we're trying to do is we try to find the root, which will give us the time constant. So we get rid of it. Then we solve for S, which happens to be minus R2 over L, which means that the decaying exponential will be minus T R2 over L. Now, that's not very formal. That's a really quick and dirty way to look at it, but that's probably the fastest way to the problem. So here's the complete response. We started at 0, we ended at I naught, we have this exponential approach, right? And how long is controlled by R2 divided by L. Now remember, that means the time constant is actually 1 over this, so it'll take 5 times the inverse of this to get where we're going. R2 divided by L would have units of frequency, which is 1 over second, which would make the units match here. Now, that would be, in my mind, the quickest way to solve that problem if you just hadn't memorized um, the time constant of an RL circuit, and because otherwise you could just look at it, oh, it starts at 0, ends at I naught. If you know the time constant, then you can just write it out. But um, even after a week, I tend to forget what that is because I just don't use it that much, right? So I usually end up solving it out. Now, for those of you that would like a more formal way of doing it, all right, we have our currents, we have our voltage drops, we have equation 1, where the current through the resistor of R1 equals the sum of these two currents. Then we say R1 is I naught divided by S, because we're going to use the Laplace method. When that switch opens, it's like a step, instead of a step voltage, it's a step current, and it's scaled by I naught. Now, what is the current through R2 in Laplace? It's just V divided by R2. What is it through the inductor? V divided by SL. Remembering that the impedance of the inductor is SL, right? And then for shorthand, I've just said V equals VR plus VL. Put all of these into equation 1, and we get I naught divided by S equals to the voltage, right? I multiply through by S to get this equation. Okay. That's where we started with on the last slide. So then I solve for V, which is I naught divided by this combination. And then I find, well, what we really were looking for IL, not the voltage. So that's really the voltage divided by the impedance of that inductor. And I have I naught SL times this relationship. Now this might look a little funny, and so I want to put it into a more recognizable format. And so what I'll do is I'll pull out this R2, right, so that I get S plus R2 over L. And notice there's my time constant from the previous solution, or even though this is in units of frequency, but that gives me my time constant. So the thing is let's break this equation up. 1 over S, right, means there's a step function in there somehow, which means we're going to get an exponential approach. Then I have I naught scaled by something divided by what the inverse Laplace will give is a decaying exponential. So yeah, you would have to use partial fraction expansion, but if you do these so much, you'll realize that it's just I naught divided by S minus I naught R2 divided by L. And when you take the inverse Laplace of this, well, you just get I naught. You take the inverse Laplace of this, and you just get I naught e to the minus t. There's your R2 over L, right? Which then would give you the formal response. I leave it to you to do it however you would like to do it. Most likely, the first method I showed was probably the quickest and the best for the 101 exam.